Hello, we are back. We are eagerly awaiting finding out exactly what, well, this strange new object in the outer solar system looks like. It's so good to see all of you here. And Michael, I think you decide what to drink based on what we learn about the MU69 2014 flyby and what exactly it is that this strange weeble wobble shaped object actually is with the high resolution images. Now I'm going to real fast finish tweeting this as they go live. I think they're going live. They're doing something.
Good afternoon. Welcome to the Johns Hopkins University Applied Physics Laboratory in Laurel, Maryland, where a new world is being revealed before our very eyes. NASA's New Horizons spacecraft is giving us our first close-up look at the Kuiper Belt object Ultima Thule. I'm Mike Buckley from APL Public Affairs. Today I'm going to introduce you to the team members from New Horizons who will be bringing these discoveries to you. We are going to take questions from the audience here and the media and over the phone. And also make sure you're following us online at nasa.gov and at pluto.jhuapl.edu. Now, the team members who will be speaking about these findings today are Alan Stern, New Horizons Principal Investigator from Southwest Research Institute, Kathy Olken, Deputy Project Scientist from Southwest Research Institute, Carly Howlett, New Horizons Co-Investigator from Southwest Research Institute, and Jeff Moore, the New Horizons Geology and Geophysics Team Lead from NASA Ames. So each of the panelists will make a statement, and then we'll open it for questions. So, Dr. Stern.
Thank you, Mike. It's great to be here. You know, it was just a day and a half ago, barely 36 hours, that New Horizons swept down over Ultima Thule in a technical success beyond anything ever attempted before in spaceflight. And this is a candid picture in the room, in our geology and geophysics room, just as one of the first images came to the ground from that flyby. And you can see how happy people are. I don't think we've stressed enough, and so I really want to say what this spacecraft and this team accomplished is unprecedented. The object that we rendezvoused with at midnight on New Year's Day wasn't even known until the summer of 2014. And we had to use advanced tools like the ESA Gaia Observatory and the Hubble Space Telescope to get its orbit well enough to intercept it at a precise place and moment in time at a speed of 32,000 miles an hour. And it's only really the size of something like Washington, D.C., and it's about as reflective as garden variety dirt. And it's illuminated by a sun that's 1,900 times fainter than it is outside on a sunny day here on the Earth. So we were basically chasing it down in the dark at 32,000 miles an hour, and all that had to happen just right, as did the entire sequence. And you can see how happy people were. And that's the result of all of their hard work, but it's also a result of the spectacular results that we're about to show you. And everything that we're going to tell you is just the tip of the iceberg. We have far less than 1% of the data that's stored aboard the solid-state recorders on New Horizons already down on the ground. But I want to show you what elation means and what it means to be a team. Now let's get to the science. Well, here's where we were just a couple days ago on December 31st, 2018. This was humanity's best image of Ultima Thule, made by New Horizons at a range of about 500,000 kilometers out. Well, that image is so 2018. Meet Ultima Thule. Just like with Pluto, we could not be happier. What you're seeing is the first contact binary ever explored by spacecraft. It's two completely separate objects that are now joined together, and you're going to hear a lot more about that from Jeff Moore in just a little bit. Before that, I'm going to tell you a little bit more about it, and then Kathy Olken is going to add to the story. I'm telling you about its rotational properties and about albedo variations or reflectivity variations we see on the surface. Carly Howitt is going to tell you about, she's going to show you the first color images of Ultima. And then tomorrow we're going to show you even more because stereo's coming to the ground, composition information's coming to the ground. We're looking for the atmosphere and that data's just landed. So we'll have a lot more to tell you tomorrow as well. But let me say, that bowling pin is gone. It's a snowman, if it's anything at all. And, you know, we have to start thinking about some provisional names, and particularly we need names right up front for the two lobes so that we can refer to them individually. Now, being scientists, we're not all that creative with words, so what we've decided to do is name one lobe Ultima and the other Thule. The big one is obviously Ultima. It's pretty easy to remember. And I want to talk about one more thing before I turn it over to Kathy. You remember that in the summer of 2017, one of the things that we did to pin down the orbit and so that we could intercept this amazing place in space was called the stellar occultation, in which we actually had to put a couple dozen telescopes in the shadow path of this tiny little city-sized world from 4 billion miles away. And we predicted where that would be if we knew the orbit precisely right. It was down in southern Argentina. And in fact, we managed to get that just right. And as you can see, some of those telescopes actually saw the light of Ultima blocked out, and that painted out a silhouette. And as a result, we learned something about Ultima's shape, and we were able to precisely pin its position in space at one precise moment in time, using another technology called GPS satellites. This is part of what went into this amazing success of being able to do what New Horizons just did earlier this week. But I want to put the cherry on top and show you how well that occultation profile fit the actual target when we actually resolved it with the LORRI camera. How's that? Go New Horizons. Go NASA. Kathy.
Thank you, Alan.
I think we can get this out now.
Yeah. So this is our model of our bilobate comet, and I'm going to tell you about the rotation period of Ultima. Now that we have new data down, just in the last day, we now know that Ultima rotates with a period of 15 hours, give or take 1 hour. And now that we have this information, that's helped us to understand the mystery and further reveal what's going on with the light curve on Ultima. This animation shows the rotation of Ultima the bilobed object there, compared to an ellipse. So when you have two spheres rotating, you're still seeing the same surface area, so there's less variation, and then compared to an ellipsoid, as it would vary, you're seeing a different projected area. So this bilobe shape combined with the other information means that we really fully understand the rotation period and the light curve now. I also want to tell you about the reflectivity of the surface. So we see the light that we see on Ultima is reflected from the sun, and we can see different brightness variations depending on how bright the surface is. So the brightest areas reflect 13% of the incident sunlight, and the darkest areas reflect only 6% of the incident sunlight. And just like Alan told you before, this is very dark. This is like potting soil. So this is a very dark object, but it shows a significant variation, a factor of 2 in brightness across its surface. One very interesting feature is the neck that connects the two objects in the contact binary. That shows it's one of the brightest regions with a reflectivity of 13%. And that's consistent with having fine-grained materials that have settled there due to gravity and slope. We also see variation in each of the lobes. So the lobes show variation also from of a factor of 2. And some of that is right next to each other. The brightest region and the darkest region can be seen right next to each other in the upper Thule lobe of Ultima Thule. And next, I'm going to pass it on to Carly.
Thanks, Kathy. Oh, that went too far. Hi, I'm excited today to introduce you to the color of Ultima Thule. So on the left-hand side, you're seeing an enhanced color image. So this is the near IR, the red and the blue, taken by the Ralph instrument, the MVIC, part of the Ralph instrument. In the middle, you're seeing the lorry image that we've already discussed. And on the right-hand side is the color image overlaid onto that lorry. We had a rough color from Hobble, but now we can definitively say that Ultima Thule is red. Yay! This color is consistent with other objects in its class of a cold classical Kuiper belt object. Both lobes, Ultima and Thule, have similar colors, but the neck region, as Kathy has already described, is not only brighter, but it also is notably less red. We have other data sets which will be downloaded over the course of the next 2 years, and those are going to tell us a little bit more about the smaller scale variations of Ultima Thule. These color trends provide us an important clue as to the formation mechanism of Ultima Thule, as Jeff is going to talk about in a moment. Okay, so when we compare Ultima Thule to the Pluto system, we find that its coloration is a lot like the Maurdor macular region of Pluto's large moon Charon, although, as this slide shows, it's notably smaller and less dark. Our current theory as to why Ultima Thule is red is the irradiation of exotic ices. And with that, I'll hand over to Jeff.
Thanks, Carly. Okay, let's start right away. Okay, so first of all, let me let you all know this is actually a new image. These images just became available in the last 12 hours or so, and they're higher resolution. So we'll see some things you couldn't see in the pictures we just saw in the last few minutes. I want to say about this image and the image and other images we've seen is that they're all very high sun images. They're taken basically with the sunlight coming in from behind the spacecraft, so there aren't any real shadows showing in any of these images. However, as we downlink more data, we're going to get higher resolution views, and also the sun angle is going to change, and we will begin to see very high resolution, maybe 4 times higher than this image, for instance, and a much better sunlight or illumination of the actual landforms and textures of Ultima Thule. So stay tuned. We'll give you a much, much better description of the topography and the landforms in future press conferences and other reports. Okay, so with the images we have in hand, this image is about a native resolution of around 150 yards per pixel. You can see that you have a modeled appearance of the overall landscape of Ultima and Thule. The yellow arrows point to brighter features, which are often circular dot-like as opposed to being elongate. And that's in contrast to the darker regions, which the red arrows point to, which often seem to form elongate patches or streaks, or however you want to think about them. There's this remarkable neck feature. It's just been discussed. Carly and others have mentioned how it is less red in these grayscale images. It appears to be higher albedo. And that could be due to two processes. The higher albedo could be due to the fact that material has collected down there small particles, and smaller particle material is often brighter just by the nature of being small. Or alternatively, it could be the consequence of different compositions, but we'll be able to have answers to those questions very soon. There are presently in the images we have available no obvious impact craters, and there are suggestions of hills and ridges, which when I go to the next slide, we'll talk a little bit about those. But again, all these features are being inferred from essentially no real direct topography yet. However, comparing this image with the image that was shown earlier in this press conference, there's been a slight change in the aspect or the viewing geometry of the two image sets. And between the two image sets, we might be able to derive some topography, which will be the discussion of tomorrow's telecon. I'm sorry, press conference. You see what my life's like. Okay. Okay, so let's talk about what we can say about the topography. Well, we can do limb topography, and from limb topography, and let's look at this, the lower portion of Ultima Thule. In the case, this will be Ultima. If you go from A counterclockwise to B, here's a plot of that where what we've done is we've taken an ideal elliptical shape, which is what the blue ellipse on Ultima is, and look at the deviation of the actual limb, which is the pink line, which runs from A to B. So when you look at the deviation, what you see is there are changes in elevation greater than a kilometer, which probably I should say it's also greater than a mile. So we can see that we have changes in shape which are on order of a few percent of the entire diameter of the Ultima lobe. And it's interesting that looking at these profiles, there is a suggestion that we could just as easily be seeing positive topography as negative topography. And by that I mean we might find that Ultima Thule is more dominated by or has a substantial component of hills and ridges as opposed to just craters. For instance, let's look at at Thule, the upper lobe. You can see the two red arrows point to basically what look like divots along the limb. And then there's seemingly a dark band which seems to connect these two divots. And if that in fact is related to a change in topography, it might imply that the feature that's basically on the top of, in this perspective, on the top of Thule might be a plateau. But we'll know so much more when both of the reports we can give you tomorrow from the initial stereo analysis as well as the information we'll get from subsequent imaging. Okay, in fact, we have one way to think a little bit about surface slopes already. Team member James Keene has developed very quickly a computer model, which you can see on the right, where he's been able to determine that the highest local slopes, if you were a particle setting on Ultima Thule, where would you be on a steep slope? And you were in fact setting on a steep slope if you're on one of the two locations near or at the neck of where the two lobes come together. And the yellow indicates where you're at an angle so high that you'll basically start rolling. So perhaps an explanation for the bright band we see that connects the two lobes is in fact loose material which is simply rolled down to this local circular ravine, for lack of a better way to conceptualize it, which makes up the connection between the two lobes. May I have the next slide, please? I was up all night, sorry. Okay, so let's talk about the formation of Ultima Thule. So we think what we're looking at is perhaps the most primitive object that has yet been seen by any spacecraft and may represent a class of objects which are the oldest and most primitive objects that can be seen anywhere in the present solar system. What we think we're looking at is the end product of a process which probably took place in only a few 100,000 or maybe a few million years at the very beginning of the formation of the solar system, where initially you have innumerable small particles or pebbles, if you want to think of them that way, that swirl together into little nodes. And as these nodes swirl together, the processes of low velocity collisions, or in some cases gravitational interactions with these little particles will fling the particle out, which causes the so-called angular momentum, the rate in which things spin around in a circle, to decrease. And so this process would operate initially to bring a few large clumps together. Maybe that's how Ultima and Thule, separate objects, formed. And then as the last few bits and pieces of their local eddy or swirl are ejected or else collide with other objects or with them, the amount of energy that's still left in the system is so little that the two lobes come together. And I want to bring to everybody's attention that this coming together, the lobes would be at an extremely slow speed. It would be like about maybe 1 or a few miles an hour, the speed in which you might park your car at a parking space, or if you had a collision of another car at those speeds, you may not even bother to fill out the insurance forms. So the real bottom line is that both the nearly spherical shape of the individual lobes, as well as the fact that two lobes come together so perfectly without any basically collisional damage, hence no need for insurance, is a strong indication that it's all formed through accretion and accretionary processes as opposed to some other mechanism. And so what we're looking at is basically the first planetesimals. And from these first planetesimals, where they're more commonly found, or where they were more commonly found in the inner solar system, came together to form the planets and the moons and everything else we see. But these are what's the only remaining basic building blocks in the backyard of the solar system. We can see that everything else that we live on or see through our telescopes or visit with our spacecraft were formed from. So I think we should think of New Horizons as a time machine, like the Wayback Machine, which we set to time 0. And that has brought us back to the very beginning of solar system history, to a place where we can observe the most primordial building blocks of the planets. And with that, I'll turn it over to Dr. Reppuken.
So, before we take questions, I'd like to introduce Dr. Thomas Reppuken. He is the Associate Administrator for NASA's Science Mission Directorate.
Well, I'm so excited to be here. Mostly, frankly, what I want to do is bring you regards and gratitude from a New Horizons fan, my boss, the administrator, Jim Bridenstine, who wanted to be sure that I hear and really tell you about the gratitude that he has on behalf of our entire team for what's being achieved here. So I really want to thank you for that on behalf of our entire NASA team, and especially Jim. I want to remind you, when I look at these pictures, that I really think of it as the essence of exploration. A question that comes from classes that I sat through in school many, many years ago about what are these original objects really like. A question like that turned into exploration, turned into knowledge, and a process that's just starting right now, a process that, compared to the whole body of data we're going to get here, is only just a small percentage. And so I'm just so excited to think of that as something that ties us together, exploration. Exploration being all about hope and all being about the courage to do these kind of things, these kind of risks that Alan talked about earlier. I think of this also in a way, if I look at all the 100 missions or so that we're currently working on, I think of it as a breakthrough in a very different way. Recall that, of course, New Horizons stands off the shoulders of Voyager and other missions ahead of it, but it was done in an entirely new way, in a different way, in an innovative new way, run by a principal investigator team and with an organization like Applied Physics Lab and their industrial partners, for about 20% or so of the cost of Voyager. That gives us hope too, because we think of this as just the essence of these new frontiers missions that some of them are out there already, and many of which we're thinking about going into the future. So I really want to thank the team on behalf of all of us at NASA and really say go New Horizons, go NASA, and go exploration forever. Thank you.
I'd say thank you, Dr. Reppuken. And now we will take questions from the media here in the audience. And I think we also have some phone calls too. We'll start here in the auditorium.
Hi, it's Bill Harwood, CBS News for Jeff. Looking at those pictures and looking at the neck specifically, is there any way to even guesstimate how strongly bound those two lobes are? I mean, it almost looks like you could break them apart pretty easily. I mean, is there any way to make even a guess at that? Thanks.
Well, that's a fair question. We think that they are, in a structural sense, soundly bound in the sense that you probably couldn't walk up and push them apart yourself. But they obviously came together at such a gentle speed, as I said, maybe a mile an hour or a few miles an hour, that they really are sort of resting on each other. You can kind of think of it as analogous to a spacecraft docking of another spacecraft, almost more than you can imagine it being any kind of collision.
And if I can add to that, we've already done the calculation to compare the centripetal force of that 15-hour period to the mutual gravity of these two lobes attracting one another, and shown that the mutual gravity is substantially larger. And so their gravity alone can hold them together, and even without any mechanical forces adding to that.
Okay, another question here in the auditorium.
Hi, Chris Lintott from BBC Sky at Night. Question for Carly. It looks like there's some color variation in the image. Could you say something about how that might have happened, or rampantly speculate about what might have been going on?
So the two lobes, Ultima Thule, do look the same within error. And so there's no variation significantly there. The big variation is on the with the neck region, and that's less blue. But at the moment, this is the first time we've processed it, so we'll be getting a lot more data soon, so we hope to be able to say something more about the small-scale color variations in the next few months. But I think that's all we're willing to put money on right now.
Okay, we'll do one more here, and then we'll go out to the phones.
I'd be curious to know what's the biggest surprise from what you've learned so far, and how much bigger do you think is Ultima versus Thule? It's hard to tell. Is it like 3 times the size, or maybe some scale references besides just the length?
Yeah, those are great questions, Marcia. And in fact, if you take their individual radii that we've now measured by fitting ellipses to the profiles of each of the two lobes, and then from that calculate their volumes, it is almost exactly 3-to-1, your guess, between the small one, Thule, and the larger one, Ultima. And you had another question? Surprises. Well, as the principal investigator, I'll say I'm surprised that more or less picking one Kuiper Belt object out of the hat, that we were able to get such a winner as this, that's going to revolutionize our knowledge of planetary science.
All right, so we'll go to the phones, and at the same time, if you could also state your name and your affiliation before you ask the question.
This is Leo Enright with Irish Television. Congratulations. I know, Alan, that Kenneth Edgeworth would be very proud of you today. But I have a question about this contact binary as it being the first. Was Churyumov-Gerasimenko also theorized perhaps to be a contact binary, or am I misunderstanding?
Jeff, you want to take that?
Well, I'll try. I think that, if I understand your question, is how common are contact binaries? Is that what he was asking? Let's say that was your question. Okay. So, as you say, a number of people have done studies to understand the evolution of features in the outer solar system, and it seems that contact binaries form commonly enough. It's interesting when you look at, for instance, comets that visit the inner solar system, which we've sent spacecraft now to several of them. They're quite commonly bilobed. Now, there's been a big controversy on how those lobes form. Are they entirely a sublimation feature? Is that to say they're due to the evaporation away of the material which they're made of, or are they actually some sort of primordial shape which has been massively eroded? But anytime we see comets, we have to remember they're post-toasties. They've been, fried and crackled and crunched by the sun, and they're badly damaged examples of former Kuiper Belt objects. And so, being able to go out and see a pristine Kuiper Belt object tells us now that indeed contact binaries really do form, and maybe when we see comets, we're looking at smaller versions of very badly damaged contact binaries.
And if I can just add one thing, I think that this is the first object that we can clearly tell was born this way and didn't evolve to simply kind of look bilobed, that formed in this very gentle accretion environment that Jeff described, and that hasn't evolved in all this time, as we talked about in the pre-flyby briefings, because it's so small and so cold. And so this really puts the nail in the coffin now. We know that this is how these kinds of objects in many cases formed.
Can't believe we have a follow-up on the phone, too.
Yeah, thanks for clarifying that. My other question was to do with the comparison of redness between Charon's North Pole and this object. My understanding was that Charon had this color due to deposition from Pluto through some sort of complex interaction between the two bodies. So I'm wondering, does this make you wonder again about the origins of Charon's redness? Or can you even wildly speculate, to quote my colleague, about how you end up with such redness also on this body, which is completely away from any large object?
So we think that while the coloration is similar, the color ratios are similar, the processing is different. We still think that Charon has this redness on the poles because it's sort of getting volatiles from Pluto's atmosphere that are kind of cold trapped on the surface of Charon. And that's clearly not the case on Ultima. I mean, there's probably something from the matter that it formed from that could have had those volatiles in, which have slowly been irradiated or from different maybe types of particles and changed. So the process by which it got red is sort of similar chemically, but that doesn't necessarily mean that the essence of that volatiles is the same. Does that answer your question? I think that's right.
I'd like to add to that.
Sure.
So there's many different ways to make red material. And the red material that we see on Mordor Macula in the North Pole of Charon, we have one explanation for how the volatiles got there and how they were processed. The volatiles escaped from Pluto, landed on Charon, became cold trapped, and were irradiated over time. That is consistent. The process that we were just talking about could be the same thing that happened on Ultima. There are also other processes, perhaps the smaller particles that then accreted into Ultima became red earlier. So organic material can appear red, and so there's a number of different ways of going at this.
Okay, we'll stay on the phones with the next caller, and then we'll come back to the auditorium.
Hi, this is Lisa Grossman from Science News. I have a question for Carly and a question for Jeff. For Carly, can you say more about those exotic ices? What do you think they are? And for Jeff, is the resolution good enough at this point to say anything about whether Ultima Thule has any craters at all? Is it lacking craters? Are they just very small? And what does that mean?
Carly, you want to go first?
So this is Carly, I'll go first. So we don't really know. We think it might be methane, it might be nitrogen. We have LISA data coming down soon, and so we hope to be able to give you a definitive answer, maybe by tomorrow, maybe later. So stay tuned.
And one word on the LISA data that's coming down. So there's data coming down right now. We had to bring down only selected wavelengths, so we will have some parts of that answer tomorrow, but it'll wait the full data downlink until we can get the full answer and be sensitive to all different species that we can look at in the infrared.
Okay, as I said earlier in this briefing, we've seen no unambiguous evidence for craters on the surface of Ultima Thule, but almost certainly I'd be surprised if there aren't at least a few. Now, theoretical study suggesting what the crater rate in this part of the solar system, the cold classicals, might be, suggests that Ultima Thule could be very underpopulated with small craters in comparison to, say, the asteroids or something in the inner solar system. So we may discover it doesn't have very many craters. In fact, we may very well find that most of the texture is dominated by, again, these very slow motion accretional processes, as opposed to the higher velocity processes which produce impact craters.
And I'd like to add, just to sharpen up so we don't get any misreporting due to our not being clear, we're not saying there aren't craters on Ultima or on Thule. What we're saying is the lighting geometry on approach with the sun behind the spacecraft's back makes it hard to see whether the features on the surface are craters or not. And as we fly around the side of Ultima, we'll get that view with what we call higher phase angles, which means more shadowing. And we'll be able to make a definitive determination, and ultimately we'll count the number of craters as a function of their size to understand the impactor environment. Unfortunately, the approach images that we're showing you that came down first just aren't conducive to determining whether there are craters on the surface or not.
Okay, so we'll go back to the auditorium.
Hi, Dave McDonald with The Sky this month. Realizing we do have 20 more months of data to come, but so far, do we have anything that would confirm or alter our thoughts about the formation of the solar system or planets in particular yet?
Okay. Well, it's actually gratifying to see these almost perfectly formed contact binaries in their native habitat. People have speculated for a long time that processes, such as the process that was illustrated by the sketches I showed you earlier this afternoon, might be how the initial primordial clumps come together to form the what's called planetesimals, which are the things which in turn go on to make the planets. But to actually see the things that in fact are consistent with the explanations that we have and theories we've had for how these things form is extremely gratifying. So to zeroth order, our ideas of how these things form seem to be somewhat vindicated by these observations. But of course, as was alluded to before, actually studying the details of how Ultima Thule is shaped and was formed will go very far to clarify the details of that formation processes.
Okay, we'll stand here.
All right, guys, Mark Strassman with CBS. I have a question about the pictures. Do we have a sense yet of how many there are in total? When and from how far away this one was taken? And then once we get closer, how distinctive will the topography become?
Okay, that's easy to answer. As Alan had just mentioned, that as we get closer and closer to the target, the sun illumination will change. Instead of having the sun shine straight onto the target like it is in the images we showed you today, the sun will be moving over to the side, and so you'll have lengthening shadows and hills and dales and craters if they're there. They'll begin to express themselves, and at several times higher resolution than you saw in the images that we displayed today. So the combination of higher resolution, much better lighting, and the fact that the presentation of Ultima Thule will change as the spacecraft flies past it will allow us to also generate very high resolution topographic maps. So we'll be able to tell you precisely about the shape and sizes and origins and processes which form the landscape.
And
you go first, then I'll take it.
Okay, and I just wanted to add some quantitative details there. So the highest resolution image that we showed today is about 140 meters per pixel. The slightly lower resolution is a little more than 300 meters per pixel, and our highest resolution that we will get down later, we don't have on the ground yet, is expected to be about 35 meters per pixel.
Yes, so what she said. But I'll just add, the current best picture that we have I believe has 20,000 pixels or 28,000 pixels on the target, which way beats the 6 pixels we showed you last time. Okay, we're in a different regime now. But ultimately, if everything worked just right in that stretch goal observation that we call CA06, or the close approach observation 6, the highest resolution image set that we took, that Kathy was describing, that'll have 35-meter resolution, will ultimately be a megapixel image. So it's going to just get better and better. And in total, you asked about how many images. We take images different ways. We have the color and the panchromatic. And as we do the very close approach observations, we're going to be taking several dozen. If you add up all the various kinds of resolved imaging that we'll do, including the imaging for spectroscopy, where we actually map the surface composition at all these different wavelengths, there will be hundreds of images in the end. And I think we've got 4 on the ground, or possibly 3.
And when and from what distance was this photo taken?
The better of the ones that you saw, the one in Jeff's presentation, was taken from a range of, I think, about 50,000 kilometers, maybe a little bit closer. And so it was still something like an hour before closest approach. We can get you those numbers.
They're in the release today. Still there.
Stephen Young with Astronomy Now magazine. Your photos from the science team room showed us the excitement today. What's it going to be like tomorrow? And what missing parts of the puzzle that are coming down right now are you most looking forward to seeing?
Well, I think that each scientist on the team has their own biases as to what they're most looking forward to. Personally, I think we'll just go right down the row and each person can speak to it. I'm looking for getting the satellite search results. You know, Jeff showed that swarm of objects that we think were the Ultima Thule system early on, and which ultimately coalesced into the 2 lobes. I'd like to know whether or not any of that material at all is orbiting, even as objects that are just 100 or 200 meters across. Kathy?
Yeah, thanks. I think the real excitement today is going to be in the composition theme team room. Right now, as we're speaking, data is streaming in on the LISA data, which gives us our composition information so we can map the surface composition. And we're all very interested, or maybe it's my own bias, but I'll say I'm very interested in understanding what the surface composition of this object is. There's no way to make anything like this type of observation without having a spacecraft there. It's why this exploration is so critical.
I share Kathy's bias. I'm excited for the composition coming down this afternoon. I'm also excited in the future to, of course, get high spatial resolution color. But yes, I think the excitement's with composition today.
Well, wearing my geology hat, I'm going to say, of course, what we're really interested in our group, the geology imaging group, is to take the images we already have on the ground, and we already have the first batch of images down, and we won't get additional images until about a week or so from now. So we're taking the images we do have, and as I mentioned earlier, the two images are taken at slightly different perspectives, and so by going back and forth between the perspectives, we can probably, using geometry or trigonometry, map out local highs and lows and get some understanding of if we're seeing craters or we're seeing hills. And that's going to be what we're really going to work on, be cranking on this afternoon and overnight, and hopefully we'll have a presentation for you on what we discover tomorrow afternoon.
Okay, so I understand we have a couple more phone calls. Let's go back to the phones.
Oh, hi. This is Dave Mosher. I'm a science and technology correspondent with Business Insider. I have a question about, firstly, what comes after this? Maybe it's a bit premature, but New Horizons is still moving along very quickly. Do you hope to reach another target, and approximately when? And then also, I understand you took some images from behind MU69. What do you hope to get out of those images in its shadow? Do you hope to see an atmosphere? Do you expect that? And what might that tell you? Thank you.
Yeah, I'll take the first part, and somebody else can pick up the second part if they like, or I'll answer if nobody volunteers. I think the first part of your question was about, what was it about? I'm thinking of the second part.
Next target.
Yeah, the next target. That's easy. I love that subject. Yeah, as background, New Horizons is a very healthy spacecraft. In fact, all the systems on board are redundant. And we're not using any of the backup systems because we've had systems failures, even though we're 13 years in flight. So spacecraft is in peak health. It has power on board the nuclear power generator to operate for between 15 and 20 more years, and therefore to travel out to about 2.5 times its current distance from the sun and explore much further. And we have the fuel to do that too. Now, the key to the science that we do is whether it's science studying objects remotely with our telescopes, or whether that science in the Kuiper Belt also will include one more flyby. And I can't give you the answer today because we don't know. We've been very careful during this period of 3 years where we were planning every detail of this flyby to stay focused on that and not get distracted by the next shiny thing, if you know what I mean. So, in fact, the Planetary Mission Senior Review will call for proposals in the summer of next year, 2020, and we'll propose to NASA an exciting program. And then if that proposal is accepted, we would start a search for an object that we could fly by. Now, the Kuiper Belt is vast. We're currently at 44 astronomical units from the sun, each of those being the distance from the Earth to the sun. So we're 44 times as far out as the Earth. And the extensions of the Kuiper Belt go out as far as about 70 astronomical units, and we won't be there for almost a decade. So there's plenty of time to go find other targets if we're in the position of having a still healthy spacecraft, an accepted proposal, and our search is successful. So stay tuned.
Okay, and I think we had another phone call.
This is Kelly Beatty from Sky and Telescope. I am just amazed at these images. Can someone address, now that you know the shape and the rotation pole, what fraction of this you will not be able to see because it will be in shadow all the time, even as you get behind it?
I can tell, Kelly. You want to tell?
I can speak a little bit, and you can add to that. So we know that the rotation pole is tilted about 30 degrees away from the line of sight between the spacecraft and Ultima. And so we're seeing a little bit more than half of the target as it rotates. We haven't seen all of that yet in high resolution, but we'll get that down as the days and months continue. But we're getting a little bit more than half.
Yeah, and I can tell you that on a flyby like this, when you don't know the rotation period in advance and you can't plan for that, you can't predict exactly what you're going to get. And now that we, in the last day or so, have got this roughly 15, 16-hour class rotation, we can tell that this is actually a pretty good case, and we're going to get more than the minimum by quite a bit. But we can't give you an exact number just now because the error bars on the rotation rate are still substantial enough that we can't get the precise number.
Okay, we'll go back to the auditorium.
Just thought the panel might be amused to know that although you're comparing this to a snowman, the Twitter is also have concluded it's in fact BB-8. But its spherical shape has already struck me as a lot more spherical than what was predicted. And I'm wondering if that comes as a surprise to you, and does it suggest anything about its potential self-gravity?
You take that?
Yeah.
Okay. Well, yes, we were also surprised about how spherical the two lobes were, and we right away came to the conclusion they could only be explained by the aggregation or collection or slow coming together of numerous smaller objects, and basically it's an aggregate or accretional surface. And it's really hard to imagine how you could get a sphere by any other means other than through this slow collection of particles from some localized swarm. So to say it was unexpected might be false because we understood that if the situation I just described was in fact how these things form, they would in fact be spherical. So it confirms one of the several explanations or ideas people have on how planetesimals, the building blocks of planets, come together. I think that answers the question, I hope.
Yeah, I would just add that, this is how science works, is that The theorists have ideas, they do computer modeling, they think hard about problems, they take the available data, and different models produce different outcomes. But then you need more data in order to distinguish between those models. And in the last 36 hours, NASA and New Horizons have collected more data on the formation of the solar system, and particularly on planetesimals in the Kuiper belt, that let us now choose between models, or at least be able to tell which models are more likely to be right than others.
And I'd like to add that, just a couple of days ago, we were talking about how we would learn about the solar system formation and evolution by looking at Ultima. And this bilobate shape is exactly what we were talking about. We didn't know what we would see, but this shape informs our models of planetary formation. You can see that they're clearly two separate objects that have come together. There's no strong neck in between each object, just like perhaps I postulated a few days ago. It's not there. It's okay. And so,
Do tweets count as publications now?
Yeah, right. So it's pretty exciting to see that. I think this is exactly what we need to move the modeling work on planetary formation forward, because we're seeing evidence right here for accreting objects and then having them combine.
Okay, we have a question here in the audience, and then we'll make one more sweep of the phones.
Hi, Sarah Kaplan from the Washington Post. Kathy, I was hoping you could talk a bit about, since the geology is giving us these insights into sort of the physics of planetary formation, is the composition and the chemistry of the object, are there particular questions that you think that's going to help answer? And are you willing to speculate a little bit on what Ultima Thule might be made out of and what kinds of things we're going to learn tomorrow?
Yeah, so that's why I say I think the excitement will be in the comp room today, because we're getting that first data down that tells us about the composition of the surface. But the color also informs us about the composition of the surface. And so we see red areas and less red areas. And the red looks very indicative of tholins, processed volatile ices that have been irradiated by energetic flux, Lyman alpha radiation, gamma rays, the like. And so that's one way to make that red material that we see. And the less red neck area combined with the high albedo is consistent with fine-grained particles that have settled into that region because of both the slope and the gravity that you would get there. And so I think we are learning a lot about the composition of the surface and the particle sizes on the surface, but we really need to have the infrared imaging spectrometer data down on the ground, and I bet it's there now.
I think they're busy.
Okay, let's go back out to the phones one more time.
Yeah, hi, this is Alex with See With Nature for Alan. There's been a lot of chatter in the last 12 to 24 hours about some of the historical associations with the nickname Ultima Thule. Can you talk about how you justify continuing to use that nickname for this object?
Yeah, I sort of thought we might get that question. You know, I've said it a number of times. I think New Horizons is an example, one of the best examples in our time of raw exploration. And the term Ultima Thule, which is very old, many centuries old, possibly over 1,000 years old, is a wonderful meme for exploration, and that's why we chose it. And I would say that just because some bad guys once liked that term, we're not going to let them hijack it. Thank you.
Okay, we'll go back to the auditorium if there are any questions in here too.
Hi, Jean-Luc Dauvergne for Ciel et Espace. It's a French astronomy magazine. When the probe was between Pluto and Ultima Thule, you have observed a lot of Kuiper belt objects to study their roughness and their rotation period, sorry. What did you learn about that? And is that similar to what you have discovered on Ultima Thule? I mean, do you think that all these objects are similar, or do you see some differences between them?
Well, we obviously see some pretty dramatic differences between Pluto, which is the size of the United States, and Ultima, which is the size of a large metropolitan area, just in their basic makeup, and you can tell from their shape. Pluto is large enough to have crushed itself into what we call hydrostatic equilibrium. It's perfectly spherical, and Ultima has these two lobes that are individually sphere-ish, but as an object, you see it's bilobate. As we get higher resolution data and the composition data and the higher resolution color, we learn more about it. I predict that not only will Ultima's landforms and composition be very different from Pluto, but even from Pluto's small satellites that are of similar size, because they were almost certainly formed in a very, very different environment in a disk of material around Pluto that resulted from this giant impact that created the satellite system. And if others want to add to that, please do.
Well, just to expand on your point that the small moons of Pluto resemble shards, like you find from a broken piece of pottery, whereas the Ultima Thule resembles two objects which came together and themselves each formed as purely accretional objects, not as fragmentary objects. And that's a fundamental difference between how the small moons of Pluto formed and how Ultima Thule and probably most, or at least very many, of the cold classicals have formed.
And then I'll also add that the 15-hour rotation period is a very typical rotation period. You don't need to come up with any odd explanations. Like if it were very, very fast, then you would have it rotating apart. And it could tear itself apart. That does not happen at 15 hours rotation period. And if it's very slow, then you need to figure out some way maybe that you could have slowed it down. So this is a very regular rotation period that we're seeing.
Okay, I think we have time for a couple more here in the auditorium.
Bobby Russell with Quest for Stars. A question on the contact zone and the ice there. Would there be any way to derive from the team the internal composition of Ultima Thule from debris frozen in that ice or layering around the contact zone?
We're certainly going to look in any windows that are available to us. By windows, I mean fissures or craters or other windows into the interior where we can see evidence of what's going on in the interior in terms of, for example, layering, or color differences or composition differences that might exist. As far as the bulk density, because the objects aren't orbiting one another, because they're physically attached, and if we don't find any small satellites that were left over from the pebble accretion swarm, then unfortunately we're not going to be able to get the density of the pair directly. We can set some weak constraints on it from mathematical models, but we won't be able to actually measure it because Ultima is just too small for us to measure the bending of our spacecraft trajectory, which is microscopic at the distance that we flew by with present-day technology.
Okay, I'm going to try to sneak in one more. There's so much to pack in this one time. We have time for one more quick question.
Hi, thanks. Ken Kramer, Space Up Close. I'm wondering also about the forces keeping it together and breaking it apart. You just mentioned a little bit about the question I had, the rotation. What kind of rotation period would you need to see for this to break apart? Well, and when will we see some data on whether there's any gas evolution? Thanks.
As far as the rotation rate, it depends upon several factors, like what are the densities of the two individual lobes, which we don't know. So we can't give you one answer for that, but we can produce models with curves that tell you for the different densities and for other assumptions what the critical speed is for the two to separate. Obviously, they're not doing that, so that provides a constraint for us. Our first calculation showed us what I said was a weak constraint because nobody expects a density this low, but the back of the envelope calculation was that for an assumption of 1 gram per cubic centimeter, basically a composition of water ice for the material, that the individual bodies can't be have a porosity that corresponds to a bulk density of less than about 0.2 grams per cubic centimeter. Hope that helped.
All right, there is...
It would be about 3 hours.
What would the rotation period be? Oh, that's for the current rotation period. You'd have to spin them up to very fast rotation periods, like Jeff said, of 2 or 3 hours.
We actually looked at that when we were still trying to explore the rotation rate, which we only determined in the last day or two. So there was a possibility of a high rate rotation. And of quickly did some back-of-the-envelope calculations and determined that if we're going, say, 2 or 3 or 4 hours, it probably would fly apart. Since it didn't, now we know it's 15 hours, we're fine. But that answers your question, I hope.
This is amazing stuff. I know we have just enough time for today, so I want to thank you, team, for bringing this information to us soon. We have one more day with more findings coming in overnight. I want to thank the audience, too, the media here, for taking on a full range of social media channels with the hashtags Ultima Thule, Ultima Flyby, and Ask New Horizons. So thank you for joining us. See you again tomorrow, and keep on following New Horizons.
So we have team members arriving at the door. I need to go. My battery's also about to die. I'm going to be writing an essay about this later because I have lots of feels. But I love you all. I'm going to go work on building a website. You are awesome. I will see you on the other side when my battery isn't about to die.